let's look at an example of how we can actually use a matrix inverse. So suppose we wanted to solve this system of equations. Well, this is written sort of out equation by equation, but remember, we can reinterpret this as a matrix equation. So this is the matrix 4, minus 3, 0, 3, minus 2, 1, minus 3, 1, minus 4, times the vector of variables x, y, z equals the vector 7, minus 2, 4. So let's call this matrix A, let's call this vector x, and let's call this vector b. Okay, so this is now A times x equals b. If we knew the inverse matrix, we could just multiply on the left by the inverse matrix on both sides. On the left-hand side, now we have A inverse times A, that's the identity matrix, and the identity matrix times x is just x, the vector x. And on the right-hand side, it would be A inverse b. So, and then we will have solved for x. So all we need to do to solve this system of equations is find the inverse. And then solving a system is as simple as multiplying your right-hand side by this inverse matrix. So let's do that. What is the inverse of this matrix? Well, you have to calculate this matrix inverse in the usual way. I won't drag you through the calculation, but it turns out that it's 7 minus 12 minus 3, 9 minus 16 minus 4, and minus 3, 5, 1. Okay, so now that we have this matrix, to solve this equation, all we need to do is multiply by b. So let's put b over here, 7 minus 2, 4. Right? And then x, the vector of variables, will be this product, whatever this turns out to be. So let's see, 49, I'm going across the first row, 49 minus 24, that's 25. Oh, and then minus another 12 is going to be 13. And then 7, so 9 times 7, 64, 63, what am I thinking? Plus 32 minus 16, so 95, 85, 79, maybe. And then minus 21 minus 10 plus 4, so 31, negative 31 plus 4, negative 27. Okay. And we did it, just that easy, as long as we have this matrix multiplication. So you can see solving a linear system really is just a matter of finding the inverse matrix for this coefficient matrix. Of course, this coefficient matrix won't always have an inverse, right? The only reason that we could do this is because this system had 3 equations and 3 variables, and the 3×3 coefficient matrix did happen to be invertible. We'll see later that most 3×3 matrices are invertible for certain meanings of the word most, but not every 3×3 matrix is invertible. So, you know, this trick of using an inverse matrix won't always work, but for this common situation, it did work. You might wonder, well, isn't it just as much work to find the inverse matrix as it is to solve the entire system to begin with? And of course, you're right. In fact, it is a little more work to find the inverse matrix than to solve the original system. So what is the advantage of doing it this way? Well, imagine that imagine you had this coefficient matrix, and you needed to solve not one equation, but many equations, all that had the same coefficient matrix, right? So you can imagine there might be tons of equations like this, all with different right-hand sides, so maybe 100. right? Would you want to do row reduction on each one of these separately to figure out the result? Probably not. But what you can do is calculate the inverse matrix just once, and then for each of these equations, calculate the inverse matrix times the right-hand side for that equation, like this, right, all the way down to the last one. A inverse your 100th right-hand side. So this is sort of front-loading the work of doing all the row reduction just by calculating A inverse, and then solving each one of these systems is just a simple matrix multiplication. And a simple matrix multiplication is actually a lot less work than doing a full row reduction for every equation. So most of the work happens, for any single equation, most of the work is happening in this row reduction, but we only have to do that once, not 100 times. This matrix multiplication is a relatively cheap calculation because it's relatively simple, and so we do need to do this multiplication once per equation, but that's okay because it's a very quick operation.